Hello guys. So in the last class we have already discussed about etching, which is a material removal technique mostly, right? Now we will be talking about material addition. So this is addition of new material, and we have different techniques for that, like deposition, or we call it coating. For deposition or coating, now we have different techniques, like how we put a new material on your on a sample, right? And for that, the first we will discuss about the most simple technique, that is called deep coating. Deep coating. So in this technique, what we do, we have the sample, right, and then we dip the sample in a suitable solution. For coating of the desired material. Okay, and this deep coating technique will depend on many parameters, like what kind of ambience we are actually doing this experiment, like what is the humidity, temperature of the ambient and of your solution, then what is the concentration of the solution, etc. And according to that, the thickness of the coating may change. So what are the example of this technique is like coating of self-assembled monolayers. On, let us say, silicon or some other substrate. So what is self-assembled monolayer? So these are the material, or these are the molecules which actually assemble themselves according to their molecular arrangement, and all of the molecules are arranged in similar fashion. Okay, so on a sample, then they coat similarly. So in this, what we can do is like one particular example is like OTS. OTS is octadecyl trichlorosilane. Okay, it has 18 carbon atoms, and it usually get coated on silicon very easily. So OTS is coated using a toluene solution. TS in toluene solution for coating on silicon. So what we do, we take some OTS which is also liquid, and then we can prepare a solution of OTS in toluene solvent, and then we just take our silicon piece and dip into the solution. Now how precisely we are going to dip and what is the speed of retraction, like while we are taking out the silicon piece from the solution, depending on all that OTS will be coated on silicon. So, this is a simple example of deep coating. Another kind of coating is called spin coating. It is called spin coating. So, in spin coating what we do, we take a silicon piece or glass piece, whatever is our substrate, let us say like this, okay, and then we put the material which we want to coat. So, like a drop, okay. So, this will be a liquid solution of the material. So, we just put a simple drop on that and then we rotate the sample with very high speed, okay. So, let us say this is the sample, then on top of that we put 1 or 2 drops of the solution which material we want to put and then just rotate this sample, and because of the rotation what happens, that because of the centrifugal forces this material spreads over the sample, right. Material spread over the sample and it gets coated almost uniformly on the sample. So, if we see the cross section image, so let us say this is the silicon piece and then after doing spin coating we will have a thin layer of the material which is coated on silicon. So, this is coated material. So, later on we will give specific example of spin coating, but before that how does the thickness of this coated material depends on different parameters. So, depends on, so there are different parameters, right. One is roughness of the sample, roughness of the sample. If the surface is very rough, then coating will not be uniform, also like it will be sorry. So, if the roughness is very high, then the coating will not be uniform and also the liquid will get obstructed on the surface itself to move, right. So, the roughness of the sample is one important parameter. Then viscosity and surface tension. So, how viscous is the solution? So, if the sample is very viscous, then with the same rotation speed it will move lesser amount towards the periphery when compared to less viscous solution, right. And also the surface tension, how the liquid sample interacts with the solid surface on which it is actually coated. So, these things are important. Then definitely another important parameter is RPM, that is rotation per minute, right. So, what is your speed? So as you increase the speed, it should spread more and the thickness should be lesser, but this has also a limitation, this is not linear. So that can be discussed in some other course. Okay, this is not part of this, but for this purpose what we should know, that if you increase the RPM, then the thickness will decrease. Then it is the wettability, which is also related to some extent to the surface tension, that how the surfaces, how the material, like whichever is coated and whichever is our substrate, like each other. So that wettability, etc., are different parameters on which the coating thickness will depend. So one example of spin coating is, just to mention, is like spin coating of PMMA. What is PMMA? PMMA is polymethyl methacrylate. So this is a polymer. So this is a polymer, and we make a solution of this polymer in anisole solution. So we use anisole, as solvent. Okay, and then we make a solution of PMMA, and then we take the sample and put this PMMA solution on at the middle, a few drops, and then rotate the sample with very high rotational speed, like something about 6000 RPM, plus we do some baking, like before and after spin coating we do some baking or heating. So after the spin coating we actually do some kind of baking or heating of the sample, so that the solvent gets evaporated and only PMMA is coated on the sample. Another important coating technique is spray coating, though it is not much used in microfabrication technique, but this is good to know while we are talking about coating and deposition. So in this case we actually make the solution and spray it on the sample, like for different kind of painting, and also sometime for dispersing carbon nanotube, etc., on a sample we use spray coating. So till now whatever we have discussed is useful for like coating of different polymers or the material which are available in liquid form, right? Whether we take deep coating or spin coating or spray coating, we are making some kind of solution of the material and then coating. Now next we will talk about how we coat metals, or which are available in solid form usually. So for that one of the most popular technique is physical vapor deposition. What is physical vapor deposition? As the name suggests, it is the vapor of the material will be deposited on the sample, and we will discuss now that how that is possible. So this has two major categories. One is thermal evaporation, thermal evaporation, and then another is called sputtering. So what is thermal evaporation? In this technique what we do, we have the material in some bead form and then we heat the material to evaporate it, and so that that vapor or the evaporated material get deposited on the sample. So for that we use this kind of setup. So let us say this is evaporation chamber, and then inside we have some kind of boat. Boat means which will hold the material, and it is some metal which can conduct current. So what we do, this is just like a metal boat, like for a kind of a holder for the sample, and this thing can carry current. This is a conductor, okay, and high temperature it can withstand. Then we apply, let us say, some kind of voltage, some high voltage to that, okay, and then the current flows in this path. So because of that this gets heated up. Now we put our material like beads inside the boat and we keep our sample, let us say, at the top. Now as the current flows through this boat, copper boat, or let us say not copper, like tungsten or some high temperature material, now this gets heated up, and because of this heating, let us say some material which is need to be coated, let us say let us assume that we need to coat silver Ag. So that silver beads are kept here. Now these beads starts melting and then starts evaporating, and that material or the vapor goes everywhere, right. As while we boil water, then the water vapor goes everywhere, and then accordingly it gets coated on the sample. It gets coated on the sample. So now not necessarily it is only coating on, it is coating also on the chamber walls and everywhere, right, but some amount of that also gets coated on the sample. Now depending on how much is the current or how much temperature we are using to melting it, then what is the distance between the boat and the sample, and also like what is the pressure inside the chamber. So we need to use very low pressure, because otherwise what will happen, that inside if we try to melt this inside air, then this will be oxidized and also will change its properties, right, and the holder also will get damaged. So because of that we create a high vacuum actually inside the chamber, and then we deposit the material, and the thickness of the material, like how much it will be deposited, depends on many things like this pressure, temperature, then material properties like what kind of material it is and what is the vapor pressure of the material, working distance. Working distance means the distance between the sample and the holders, like the boat. Using this technique, different metals like gold, silver, then aluminum, titanium, even like copper, etc. can be deposited. Now we will talk little bit about the sputtering. So actually the physical vapor deposition, the thermal evaporation and sputtering, to go details, this is a vast topic, but for the scope of this course we will not go into details of each parameters, how it controls the deposition and all. Rather we will have some idea about how these processes happens, okay, so that you will know that how exactly these materials are deposited. And if you are interested, you can learn about these techniques more in detail, so that how to control the thickness or deposition rate, etc. So in sputtering, what we do is we use a ionized gas, like let us say we can use a ionized gas like argon. Why argon? Because argon is a neutral gas. Okay, so there will be similar kind of high vacuum chamber as we have used for thermal evaporation, and then there will be a target. So there will be a high vacuum chamber, similar kind of, and then there will be a target. So target is the material which we want to coat. So let us say if we want to use if we want to coat gold on silicon, then we will be using gold targets, means this target will have already gold coated on this. Okay, then we fill the chamber with with argon gas, so the vacuum will get reduced to some extent, right, and then applying high voltage we ionize it, so it becomes argon plus ions. So this argon plus ions while applying, so this, let us say this is the sample, then we apply a high voltage in between the target and the sample, right, and then this argon plus will get attracted. So let us say this is if we apply negative electrode this side, then will be attracted towards the negative electrode, and because of that this will be kind of bombardment on the target, and because of this bombardment the target material, like let us say if this is gold, then gold atoms will get dislodged from the target and get coated on the sample. It will also go other places also, but some amount it will be coated on the sample. So accordingly we can get a gold coating using the sputtering technique. Now in real case actually we use AC voltage, and also we use magnetic field to control the movement of this argon plus ions, or to create the plasma. This is ionized gas, so this can be called as plasma, and so there are different parameters like voltage, pressure, working distance, etc. how we control the exact deposition rate as well as the deposition thickness on the sample. Also we can apply some like sample bias to attract these atoms, and also to control the surface morphology. Also we can heat it. So there are different parameters which we will not discuss for the part of this course, but this is a popular deposition technique. And the most popular sputtering technique is actually RF magneton sputtering, where we use AC at RF frequency or radio frequency, and in that case also we use magnetic field to control the movement of the ions. So that's why it is called RF magneton sputtering, and very frequently used for deposition of different metals. Now after physical vapor deposition, or PVD in short we can say, we will talk about CVD or chemical vapor deposition. So in chemical vapor deposition, what we do, we use chemical technique. That means some reactive gas will be there inside a particular required pressure and temperature, and that gas will react with the sample to deposit a particular material. For example, like while deposition of graphene, for example while coating graphene on a silicon sample, we can use this chemical vapor deposition technique. So in that case we use methane methane gas for deposition of graphene or supplying the carbon, and then at 1000 degree centigrade temperature and also at very high pressure, we can break this CH4 into carbon and hydrogen, and that carbon get deposited on the silicon sample. So actually here we use nickel, can use nickel or copper as a catalyst. So nickel and copper help to dissociate the CH4 into carbon and hydrogen, and that carbon get deposited on the nickel surface, okay, nickel surface or copper surface, and then you get a graphene film accordingly. Another example can be thermal deposition of SiO2. So at high temperature we take a silicon wafer, and at high temperature we use H2O plus O2 mixture, right. So H2O also dissociate and gives oxygen, and that oxygen at very high temperature reacts with silicon and becomes deposit this SiO2 layer. So this is called wet oxidation, where we are using actually H2O for supplying the O2, but without H2O also, just with the help of oxygen also we can do oxidation, and that is called dry oxidation. But in case of wet oxidation the growth rate is higher, whereas for dry oxidation growth rate is lesser, but the surfaces for dry oxidation is much smooth. So in some cases, like where we need, let us say 1 micron of oxide to be deposited on silicon, we can use both the wet oxidation and dry oxidation together. Like let us say first 10 nanometer of the oxide we grow it by dry oxidation. So it will be, rate will be very low, but the interface property between the oxide and silicon will be better because the surface roughness will be lesser. Now after that 10 nanometer, the 900 nanometer we can deposit by wet oxidation. So in that case the oxide quality will not be so good, like the surface roughness etc., but the growth rate will be very higher, right. So we can deposit but that 900 nanometer of oxide in very small time. Then after that the rest 90 nanometer or 50 nanometer whatever we choose, that we can again deposit by dry oxidation. So in that case the top surface will be made by dry oxide. So in that surface will be much better, and for it will be suitable for device application, and the whole oxide film can be deposited in much smaller time. Rather than that, if you have choose the dry oxidation for the whole 1 micron, then it would have taken lot more time. Now there are many other deposition techniques also, like electrochemical deposition etc., but we are not going into those details because for the part of this course we are mostly discussing the most popular techniques, and to a very short extent, like what is the basic working principle and how these techniques has been usually carried out inside a lab to get this kind of device structures. Okay. Now before so this is about deposition. So physical vapor deposition and chemical vapor deposition are the most popular two techniques for deposition, and as well as like spin coating or dip coating, these are the popular coating techniques. Now before going to the next topic, I will again revisit little bit about the material removal or etching. But last time we have talked about etching using KOH or TMH solution. So now this KOH or TMH is a liquid, right. So that is called wet chemical etching. Now after wet chemical etching we are going to discuss dry etching. So, as the name suggests, in dry etching there will be no wet part. What does it mean? Means we will not be using any liquid to etch the material or to remove the material. So, in place of liquid we will be using reactive gases. Like one kind of very reactive gas is CF4, then CF6, etc. And this also we use not only these reactive gases, we also ionize it, and that is why this is called reactive ion etching. Or in short RI. So, in reactive ion etching, what we do, we use ionized CF4 gas, let us say. So, we use only CF4 or CF4 plus oxygen plasma. So, we put these gases inside a chamber at high vacuum, and then we need to maintain their partial pressures, that how much of concentration of CF4 we will be using and how much of will be the concentration of oxygen. And then what we do, we apply some electric potential also to ionize the gas, and then this CF4 actually reacts, it relieves that fluoride radicals as well as fluoride ions, and that reacts with the silicon or SiO2. So, see, the CF4 plus oxygen plasma are used for dry etching of silicon and SiO2. Now, the etching rate for silicon and SiO2 are not definitely same, but if we add hydrogen to this mixture, then it reduces the etching rate for silicon, whereas SiO2 etching rate are not reduced by that much as it compared to the silicon. So, if we need different kind of etching rate for silicon and SiO2, let us say in our sample we have silicon and as well as SiO2, and we need more for some device application or to make some device, we need SiO2 to be etched, while we do not want the silicon to be etched. So, we can add with this mixture, we can add hydrogen, then the silicon etching rate will be reduced by like substantial amount, whereas SiO2 etching rate will not be reduced much. So, SiO2 will get etched while silicon will not get etched by significant amount. So, this is while using CF4, this is called fluorine chemistry, because we are using fluorine gas here as the main reactive gas. Then we can use chlorine chemistry also, where we use CCl4 etc. gases for the same purpose. So, that is also for etching silicon, SiO2 or this kind of material. The advantage of dry etching is it is more clean process, because we are not dipping it into any solution. So, there are some cases where we have the problem of stiction, means while we take out a released cantilever after etching, then because of the trapped water in between the cantilever film and the substrate, there is a chance that the release cantilever can snap onto the surface or can stick to the surface because of the surface tension, right. But in this case, as we are using dry etching, so no meniscus, no liquid meniscus is formed, so there is no chance of stiction for dry etching, and the etching rate is also very high, and also we can get anisotropic etching according to our choice. I mean that we can apply more voltage in one particular direction, like let us say vertical direction or horizontal direction, and accordingly we can get more etching rate in one of the directions or one of the sides. And this is not silicon property, this is not from the silicon crystal property, this is from the this will be possible even for SiO2 or other materials also, because we are changing we are giving a direction to the phenomena itself or the etching technique itself. So now, after discussing about etching and deposition, that is removing material or adding material to a substrate, we will discuss about patterning or lithography. So the first question is, what is patterning or lithography? It is like, if we consider it from its terminology, from ancient time, it is known as like writing or painting on a solid surface like stone. Now, in our context, we use lithography. While we use lithography, we want to mean that making micro or nanoscale patterns on silicon, glass or any solid substrate, other solid substrate. Now, so simply we can say that lithography means making patterns or writing patterns on something, on a piece of silicon or on a piece of glass or on a stone, like that. Now, for microfabrication we use what we mean actually lithography is a completely different technique what we use here at macro scale. So let us say I have this wood piece. So this is a wood piece and you are seeing the top view here, and this is the cross sectional view. Okay, this is a simple wood piece like this. Let us consider this is a wood piece. Okay, and this has a dimension of something about 10 centimeter by 10 centimeter. Okay. Now I want to make a square hole inside that, which hole will be about 1 centimeter depth, right, and it will have a let us say 5 centimeter by 5 centimeter arm size. So this is a square hole and each of the sides are 5 centimeter, and if we see in the cross sectional view, then let us say it is something like that, and this is about 1 centimeter. Okay. So on a 10 centimeter cross 10 centimeter wood piece, I I would like to make this 5 centimeter by 5 centimeter square hole which has a depth of 1 centimeter. So, how we can do? We can use a chisel and hammer. And definitely we need a scale or tape, right, to measure. So, it is simple like this, that we take the wood piece, then we make the drawing which is 5 centimeter by 5 centimeter using the scale, and then using our hammer and chisel we can actually remove the material from this region, right. We can remove the material from this region using the hammer and chisel. Now, assume that we want to do the same process, but in a different dimension, that is we change centimeter to micrometer. So, now we have a 10 micrometer cross 10 micrometer wood piece. Let us assume that this is not wood, rather it is a silicon piece, okay, because on wood microfabrication on wood is not well defined and it is not also part of this course. So, let us talk about silicon. Now, we have a silicon or glass piece of like the bigger size, or maybe 1 centimeter cross 1 centimeter size, but we want to make a hole in that which will be 5 micron by 5 micron of size and 1 micron of depth. Now, how we can do that? Can we use this wood, can we use this chisel and hammer? No, because chisel and hammer both are much higher dimension than the dimension we need, and another thing is that we even can't see 5 micron. So, forget about actually making a making the marking using a scale, right. So, there we need to perform lithography on a silicon substrate. So, we need to perform lithography. Now, what are the lithography techniques? So, two most common and popular lithography techniques are known as photolithography and another is called electron beam lithography or E-beam lithography. Now, what we do in photolithography or E-beam lithography, we actually use UV light for photolithography. UV means ultraviolet, okay. So, ultraviolet light for photolithography, and we use electron beam as the name suggests for E-beam lithography. Now, this photolithography or E-beam lithography, what we do, we use this laser source like UV laser source or E-beam source as just like a pen. So, we have the laser source here, and then a very focused beam comes from the pen, and then accordingly we move the pen and write on the substrate, which is on silicon, or we will see that what kind of material we actually write. Now, before we discuss about that, actually we need to understand that why we need to use ultraviolet or electron beam. That is because we have a limit with our visible light. What is that limit? That is called Rayleigh criteria. So, according to Rayleigh criteria, with our any kind of optical signal or optical light is resolution is limited by lambda by 2, almost equivalent to lambda by 2. That means, what does it mean? Means, let us say we have two particles which are separated by a distance d, then if we use a visible light of wavelength lambda, then we can actually see these two particles as separate only if this d is greater than lambda by 2. Okay. If it is not, if the d is smaller than lambda by 2, then we will see almost a merge image, something like this. Okay. So, we cannot resolve two particles separately. So, this is the physical constraint which we cannot overcome with using any kind of instrumentation. So, our visibility medium, like while we are seeing some object, we are seeing by the usual light, right, which has different frequencies, like from violet to the red, and using that we can maximum resolve in this limit. Okay. Now, ultraviolet light can have much higher frequency or much lesser lambda. So, what happens, using ultraviolet light we can actually decrease lambda of a UV light is pretty small. So, we have increased resolution. And for electron beam, from quantum mechanics we can show that from wave particle duality etc., that for a electron beam we can define its wavelength of an electron beam by this formulation, like h nu equals to EV, where E is the electron charge, V is the applied voltage. So, we can create an electron beam using a high voltage. So, for electron beam, its frequency or wavelength is defined by this formula, that comes from wave particle duality, and there we can write that h nu is equal to EV, and where nu is the frequency of the electron beam and V is the applied voltage, which is usually in some kilovolts, and then h is Planck constant and small e is electronic charge, and then we know that this nu equal to hc by lambda, where c is velocity of light or velocity of the electromagnetic radiation, right, and then we get EV. So, lambda equals to hc by E into 1 by V. So, here h, c and E all are constant, Planck constant, velocity of light and electronic charge all are constant. So, as we apply higher and higher voltage, or V, we get lesser lambda or wavelength, and that means higher resolution. So, that is why we use UV light and electron beam for micro and nanoscale patterning, because we can actually applying particular wavelength of UV light or with a particular high voltage, we can focus it at a nanometer scale, or micrometer scale is anyway achievable. Now, we know that okay, for lithography we can use UV light and electron beam, electron beam source, right. Now, what is the exact process? So, for that the general process is something like this. So, first we have the sample, and on sample we coat photoresist, or short we call PR. So what is photoresist or PR? These are photosensitive material. So these are mostly polymer, and these polymers, what happens is while we expose it, ultraviolet light, then this polymer breaks. And becomes monomer. Then this monomer can get easily dissolved in a suitable developer or solution. And get removed. So we have the polymer, let us say, then if we expose the polymer to the UV, then some whichever part of the polymer will be exposed, that part will become monomer, and then if we put it inside some kind of suitable solution, then this monomer will get dissolved and get removed. Now we can use this for photolithography. So how we are coming to that? Before that, let us give example of photoresist, and they are like AZ5214 or S1813. These are popular photoresist which are used for photolithography. And similarly, E-beam resist like PMMA. So which earlier I have discussed, like polymethyl methacrylate, this is an E-beam resist. So electron beam falls on that, then this polymer breaks into monomer and can get easily dissolved in developer like MIBK, etc. Now what are the steps of photolithography? Then we will have the sample, and on top of that we will spin coat the resist. Let us say we are talking about electron beam lithography, then what we will do, we will use PMMA. So PMMA in anisole solution, and then we will take the sample, and that PMMA in anisole solution we will put a few drops on the sample, and then we will rotate it as we have discussed for the spin coating. So accordingly this will be coated on the sample on the substrate, right, and exposed desired region to UV or electron beam. So if this is my sample, and if I need to, let us say if I need to write this pattern A, okay, I need to write this pattern A. Then what I will do, I will coat this with polymer everywhere, and then with using a laser source I will just expose only on. So I will put the laser source, I will move the laser pen such that UV pen or E-beam pen such that it will be only exposing this region, right, this shaded region, this will be only exposing this region, and the other places like these places will not be exposed to the UV or the electron beam, right. Then what we will do, we will develop it in a suitable solution. So if it is, let us say, PMMA, then we will use MIBK, which is a developer for PMMA, and then what will happen, that this region, from this A region, all the PMMA which has been exposed to E-beam and has become monomer, that will get dissolved and get removed. So because of that, only this portion will get removed, this portion, the PMMA will get removed, right, but the other regions so PMMA will get removed only from that A region, but the other region it will be still there, it will be still there. So remove unwanted part. So if this is a silicon wafer, then this region only, these regions only, the silicon is exposed, because PMMA has been removed from this region, these circle regions, right. Whereas in the other parts, like these shaded parts, there PMMA is still there, correct. So this is like we have written this A pattern in a very fine scale, like in micrometer or nanometer scale on a silicon wafer, such that the empty spaces are A space is silicon and the other spaces is that this is all polymer. Now we can do some more process, like if we etch the silicon here, using KOH etching or dry etching, then what will happen, that only according to this A pattern the silicon will get etched, but the other region it will not get etched, because it is protected by the PMMA on top of that. So these regions silicon will not get etched. Let us say I put this sample now in a KOH solution and etch it, then this region will not get etched, whereas this A region will get etched, right. And then what we will get, an etching on silicon according to this A pattern, and then we can put it in some solvent like acetone, which actually dissolves all the PMMA polymer, whether it is polymer or monomer, acetone dissolves it. So all the polymer will be actually dissolved in acetone, and then we will get a trenched in a pattern of A, right. So that we will discuss more in the next class. And before we finish actually this photolithography, what we need to note here is there, other than these steps, there is also some baking steps required, like pre-baking and post-baking. And what does it mean? Means before the spin coating also, actually we need to heat the sample to a bit, because we clean the sample, and after that some water layer, very fine water layer is formed on the silicon sample. So using baking it over let us say 150 degree centigrade or so for some amount of time, like 1 minute, we can get rid of that water layer, okay. And after spin coating also we need to bake it around let us say 95 degree centigrade for 1 or 2 minutes to get rid of the solvent, because whether it is AZ or it is PMMA, there is some solvent which is used for the spin coating, and once we get rid of the solvent, then we have the pure photoresist or E-beam resist on our sample. and even after development also we need to use baking, because development is done usually in liquid solution, whether MIBK or MF26 which is used for AZ kind of photoresist are ultimately liquid solution. So that solvent also sometimes get soaked into the sample. So for that also you can heat the sample for some time to get rid of that liquid material. We will talk about the next processes in the next class. Okay, thank you.